Hello students, welcome back. Let's go to section 3 and finally let's begin solving differential equations. Wait a minute. I take it back. We already had some experience in section 1 in motivating examples. Okay, those count, so this may not be the really beginning, but still. Let's go to some heavy-duty examples here. Okay, here is an ODE, a linear ODE with constant coefficients, and let's use the Laplace transformation method. So we're going to take the Laplace transform of each term. Y double prime plus 4 times y prime 4 times plus 4 times y equals to 2t e to the negative 2t power. Okay. Did I get everything right? Alright, let's begin. This one I'm going to name red. This one I'm going to color blue. And this one I'm going to color green. And this one is going to be just capital Y, so I don't really need any emphasis here. Okay, alright. Okay, here, do you recall the Laplace, this Laplace transform formula for the second derivative? Input derivative formula right here, s squared y minus sy and the derivative. So it's this, s squared. Why am I losing color? Never mind. Oh, never mind. Let's just start with black. S squared y minus s to the first power y of 0 minus s to the 0 power y prime of 0, and that's the formula. Now it is okay to, oh no, this is first power. Now it is okay to have s squared, s, and nothing there, but my preference is to write all the powers, including the 0 powers, so that I can clearly see that nth power, n minus first power, n minus second power, all the way over to 0 power. And that habit will be helpful if you go over to higher order linear ODEs. Okay, how about the next one? S to the first power y minus s to the 0 power y of 0. Okay, that's blue. And then black, just y, so that's just capital Y, alright. And then as for the green part, the Laplace transform of 2t times e to the negative 2t. Let's open up the table and let's find out. Let's see, where is it? Here's a summary. And then let's see, number 4, t to the nth power e to the at. Can everybody read this? N factorial over s minus a to the n plus first power. That's how it works. Over there, we have n equals to 1, first power. So this is going to be 1 factorial over s minus let's see, a is negative 2, so as plus 2 to the 1 plus 1 factor, 1 plus 1 power, so it should be second power. By the way, let's get 2 out of here, because that formula over there does not have any coefficient. T to the first power, e to the at, so 1 factorial, we have 1 plus 1 power, so second power. And then that's the green part, and then there's coefficient 2 out there. Is everybody happy with this? 1 factorial, so it's just 1. Okay, and then let's solve this equation. Let's see, we have s squared, so s squared, and then 4s, and then plus another 4 of y, that's y term. We have minuses, so let's put minuses. Y of 0 is 1, so this thing is 1, isn't it? So 1 times s1, so that's, never mind, let me copy and paste this thing again. That's 1. And then this one is negative 3. So this becomes plus 3. And then y of 0 is 1, so minus 1. Okay, all right. And then let's go to the next. S squared plus 4s plus 4y, I got that. And then minus of s, and then plus 3 minus s, and then plus 3 minus 4. So looks like I'm getting plus 1. Is it right? 2 over s plus 2 squared. Did I do this right? 3 minus 4, so this is minus 1. I wish this were in class so that students can correct me on the spot whenever I make mistake. And then let's flip this one over to the other side. So basically this is s plus 1, and then that. Okay, all right. And then I'm gonna get y equals to s plus 1 plus 2 over s plus 2 total quantity squared. And then the denominator down here is s squared plus 4s plus 4. Now, if you have to simplify this manually, good luck about that. Basically, what you need to do is factor this one. This is going to be complete square, s plus 2 total quantity squared. And then I have another s plus 2 quantity squared. So the denominator will be s plus 2 total quantity to the fourth power. So it's basically something like this. Numerator over s plus 2 total quantity to the fourth power. That's how things will turn out. And then you see you have fourth power down here. So you're going to end up with something like this. S plus 2 plus next S plus 2 squared plus C3 S plus 2, S plus 2 cubed plus C4 over S plus 2 to the 4th power, and then take the common denominators and work out, and then find out C1, C2, C3, and C4, and that's going to complete this decomposition by partial fraction. You can do it this way if you really have to do it manually, but we're not going to do that. We'll do it this way. Take that and I'll ask Mathematica to do the performance. And it appears that I'm going to get 1 over S plus 2 minus 1 over S plus 2 total quantity squared. And this one is apparently 0. And then we have 2 over S plus 2 to the 4th power. This is what I'm getting according to Mathematica's computation. And remember, the command for partial fraction is apart. Okay, finally, let us take the Laplace inversion. So, go to the table again. 1 over S plus 2. What is it? Exponential. So, e to the negative 2t. So, this one, which I just highlighted in blue, gave me that. Next, I have to do this. Let's go up here. All right, S minus A. So in order to have the second power, n should be 1, isn't it? 1 factorial, 1 plus 1. So I did t e to the negative 2t. So that's t e to the negative 2t. And that's red. And then let's go to this final term. I don't have third order term, so let's go over here. We have 4th power here, so n in value is 3. So we need 3 factorial here. Let's come back. So over here, I need 3 factorial. How do I get 3 factorial? So I have to divide by 3 here, so that multiply by 3 here, so that this is 3 factorial. 3 times 2 was there before, times 1 will not change anything, so okay. Green, so I need 3, so 1/3, and then that was n equals to 3, so t to the 3rd power, t to the 3rd power, e to the negative 2t, that's green, and I guess that's the completed solution. Well, I have complete faith in Mathematica's computation on this partial fraction, but I do not trust myself in these computation over here. So I'm not completely certain. Let's check with Mathematica. So y of t is defined as e to the negative 2t power minus t times e to the negative 2t power plus 1/3 t squared e to the negative 2t power. That's my y of t. And then simplify. the equation y double prime plus 4y prime plus 4y of t minus the right-hand side, 2t times exponential of negative 2t, and simplify it. Oh my, I'm not getting 0 here. Something is not right. This is cubic power. Is that the reason? Okay, all right. So that's a simple typo. Okay, all right. Now, this is a solution of the differential equation, all right? And how about the initial conditions? Y of 0 and y prime of 0. Y of 0 and y prime of 0. Are they 1 and negative 3? Yes, they are correct. So now I know I did it right. And here's a full solution. Let's recap. Laplace transform of each term, and then Laplace transform formula for second derivative in red, the Laplace transform for the first derivative in blue, and the Laplace transform for this constant, not constant, what do you call this, right-hand side here. And then simplification, solve for y, and then divide the denominator away to get the rational expression. And then you can do the partial fraction business, but then again, that's not something you can do. Yes, you can, but it's going to be enormously time consuming. I just gave you an indication, right? C1 over s plus 2, C2 over s plus 2 squared, C3 over s plus 2 to the third power, C4 over s2 plus 2 to the fourth power, like those. Instead of system of equation with 4 unknowns and 4 equations, oh my goodness, you could do that. Or you can learn to use computer algebra system to get the partial fraction done. That's what I did. And then by checking out each partial fraction to the table, I can figure out the Laplace inversion, which I did over here. And that's the right solution. I checked with Mathematica and it worked out.